Section 4.5 is linearization. So the idea here is that if f is differentiable at a equals x, or excuse me, at x equals a, then the equation of the tangent line, we're calling it L of x for linearization, which is y f of a plus the slope times x minus a. The approximation f of x is approximately equal to L of x is the standard linear approximation of f at a. The point x equals a is the center of the approximation. And clearly what we're talking about here is that when we have a certain point a and we do a tangent line, as long as I stay relatively close to a, the tangent line can give me an approximation of the function value. So let's take a look. Find the linearization of f of x equals cos x at x equals pi over 2 and use it to approximate the cos of 1.75. And 1.75 is close to pi over 2. Pi over 2 is 1.57, etc., etc. So we're going pretty close to pi over 2, but we're using the approximation at pi over 2. So f of pi over 2 is cos of pi over 2, which is 0, so our point of tangency, our xy ordered pair, is pi over 2 comma 0. The slope of the tangent line, f prime of pi over 2, is taking the derivative of cos and evaluating it at pi over 2 and is negative 1. So our linearization, L of x, is our y sub 2, or y sub 1, excuse me, plus our slope, and x minus x sub 1, plugging those values in, and then they simplified it to negative x plus pi over 2. So that's my linearization that I'm going to use. So approximating the cos of 1.75, which is our original function at 1.75, using the linearization, plugging this in for x, I get this value. So without having to use a calculator, I can in essence find that linearization. Okay? So here's an example of what it is. There's our curve for cosine, our linearization in red, and then showing that if I stay close, I'm going to be pretty close to that. Now, negative 1.75 plus pi over 2, I'm doing this as I speak, is actually negative 0.179203. So that's what that equals. Now if I did cosine of our actual function of 1.75, I would have gotten negative 0.178246. So you can see how close these two actually are. Okay, let's try another way to use linearization. Let's say I wanted to find the square root of 123. So my function that I'm dealing with here is f of x equals the square root of x. And since I'm trying to evaluate it at 123, and I want my tangent line to be close to that, excuse me, nope, going this way. Alright, then I am going to use x equals 121 for my point of tangency, because that's an easy function to evaluate. So, f of 121 is 11, so my ordered pair is 121 comma 11. I need a slope, so I'm going to take f prime of x equals 1/2 of x to the negative 1/2, evaluating that at my point of tangency. F prime of 121 is 1 over 2 times the square root of 121, which is 1 over 22. So using this ordered pair and this slope, remember I'm evaluating everything at 121 right now, my point of tangency, I would have L of x equals my y value plus my slope times x minus my 121. Alright, so now I'm back to finding it at 123. So L of 123 is 11 plus 1 over 22 times 123 minus 121, which is 11 plus 2 over 22, or 2 and 1, 11 and 1/11. And again, using a calculator, or if you know that 1/11 is 0.0909 repeating, I can find that value pretty quickly with a linearization, whereas without a calculator, the square root of 123 would need to be put into my I can't do that without a calculator, and that is approximately 11.0905. So you can see again how close we get using this linear approximation. Differentials. Let y equal f of x be a differentiable function. The differential dx is an independent variable. The differential dy is dy equals f prime of x dx. All we're doing here is taking dy dx, which is what we're used to doing, and multiplying both sides by dx. So what we're finding is a differential using, in essence, again, a slope at a tangent line and having a small change of x to calculate what the change of y would be. So again, looking at a curve and my point of tangency, if I calculated a very small dx and calculated the dy at that place, I could find an approximation of my using dy dx. All right, let's take a look at this. So find the differential dy and evaluate dy for the given value of x and dx. So there's my function. First thing to do is to write my differential. dy is the derivative times dx. Evaluating that at x equals 1 with a differential of 0.01, we can get a value of 0.07. This is the change from x to 0.01, which is meaning that we're going from 1 to 1.01. So let's look at this a little bit closer. If I just found f of 1, my original function, 1 plus 2 is 3, using this differential to find f of 1.01, which in my original function would be very difficult without a calculator. I would have to raise that to the 5th power, multiplied by 2.101. Again, not simple without a calculator, but over here I can say that the approximation, or the differential, at f is approximately 3.07, taking my 3 and adding my differential to it. The actual function, if I used my calculator over here, is 3.07101.005, ... So again, another way to look at finding a small change from one point to another, going from 1 to 1.01, I take the differential dy, calculated at a change of 0.01 from my original function. So if f of x is differentiable at x equals a, the approximate change in the value of f, this is the approximate change, not the new value. You notice back here, remember, we had to add that to our original 3 to get our new function value. The approximate value of f when x changes from a to a plus dx is df, the differential estimate, equals f prime of a dx. So here it is in, again, a picture showing you f of a, and this is the change of f of a plus dx minus f of a, and showing that this approximation is very close to the actual. Remember, this dx has to be very, very small. So here's an example for estimating change using a differential. The radius of a circle increases from a equals 5 to 5.1. Use dA to estimate the increase. So circle's area, there's our original function. We're going to find our differential dA, calling it 2 pi r dr. Using my original value and the differential of 0.1, I can say that my difference in area is approximately pi. So a pretty simple thing to do using that change from a to a plus dr, dx, whatever it might be. And that's it for today.